Good morning, student. Let's start today's class. In today's class, we are going to discuss some points about solar power, thermal power plant. Okay, some basic points or some fact about solar thermal power plant. Okay, first of all, let's discuss about what is storage hour. Okay, this term storage hour. What do you mean by storage hour? A storage hour is defined as the storage capacity needed to run a process at its rated power output for 1 hour. That means a storage hour is the amount of storage capacity needed. The amount of storage capacity needed to run a process uh, or a or a power plant at its rated power or rated output power for 1 hour. That means if an if an uh, power plant, okay, solar power plant rated that it can give 5 megawatt output uh, in in a hour, okay, or it can rated that it produce 5 megawatt in an hour, okay, so that so uh, for for producing that 5 megawatt power, how much thermal storage is needed? That thermal storage is called storage hour. Okay, for 1 hour, that for 1 hour operation of that of power plant, how much storage capacity needed? That storage is called storage hour. Okay, and with the annual electric energy output WA, the capacity factor, the capacity factor is another term. Okay, the capacity factor of an solar power plant, SPP means solar power plant, is remember this formula: capacity factor equal to WA by P out into 8760. Okay, WA is the annual electric energy output. Okay, and P out is the rated power of that power plant. Okay, or the maximum power output from that. The P out is maximum power output from that power plant. Okay, remember this formula. This is called capacity factor. Okay, capacity factor means the capacity of that what capacity of that power plant. Okay, if we say it in general way. Okay, now see, in ideal operation of an SSP with the storage. Now see what is the ideal operation of an SSP with storage. Let's see. Okay, this is the waveform. Okay, not waveform, this is the diagram representing the uh, the ideal operation of SSP. Okay, between sunrise at T1, this T1, okay, this is time. Okay, this axis is time. Okay, T1 means between sunrise at T1 time and the receiver startup at T2, incoming radiation is too low for startup of the receiver. That means in T1 time the sun will rise. Okay, okay, and T2 time the receiver of the solar power plant start. Okay, in between that time T1 and T2, the intensity or incoming radiation from sun is very low to start up the uh, solar collector, okay, or receiver. During tr this much, that means from T2 to T3, during tr the receiver thermal output is still not sufficient to run the conversion cycle at the rated value. That means in T1 and T2, between the T1 and T2, the incident sun radiation is very low, so that the receiver thermal receiver startup is not possible. And in TR time, okay, in TR time, the the receiver thermal output is very or is still small or sufficient, still not sufficient to run the power plant or the conversion cycle. Okay, and during TC that much, the receiver output exceed the required nominal. Okay, in TC this is the peak time of a day. Okay, means this is the peak time where the sun radiation is very much, okay, very much, and at that time the sun radiation is or the receiver output exceed the required nominal. So so input power and surplus energy charges the store system. That means since it exceed or produce excess number of excess thermal energy, so that by using our needed power, surplus energy, we can store them in our storage system. Okay, and the storage system with a and we can charge our storage system by surplus energy system with a charge utilization factor YC. This by using this factor or with factor with this factor, we can charge our or store our storage system. Okay, during during TD means this is TD. Okay, this is TD and this is also TD. From T4 to T5 also TD, and T5 to T6 is also TD. Okay, during TD the energy difference required at required to keep the cycle running at rated power is retrieved from the storage with a discharge utilization factor YD. That means in in TD time, the requirement of the thermal power for to run the power plant at its rated or rated power output, the receiving thermal energy from the sun is not sufficient, so that we can use or we use from we use the thermal energy from our storage system. Okay, and that receiving from the storage system with a discharge utilization factor YD. Okay, this is charging utilization factor YC, and this is discharging utilization factor YD. Okay, from sunset at T5 through T6, the process run at its rated power from the storage only. This T5, this is in T4 and T5, the mixing of storage system with sun radiation. Okay, this from T4 to T5, we run the power plant with incident sun radiation plus from the storage system. But in T5 to T6, this is only run by, or the power plant is only run by the storage thermal energy. Okay. Thus, with storage only, the receiver need to be designed for peak load PRE, and the cycle may be PCY. Okay, that means due to it in T5 and T6, due to this process, or due to the process is uh, running with only storage by, or with uh, by using only storage, the receiver need to be designed for peak load. Okay, and the cycle may be PCY. Remember this, PRE and PCY. Then now see what is solar multiple. Okay, the ratio of the receiver power at designed power PRE to nominal cycle input power PCY is called the solar multiple. What is solar multiple? Solar multiple is the ratio of received power at a design point, okay, that is PRE, to the nominal cycle input power PCY. That ratio is called solar multiply. Okay, multiple. Remember this formula: solar multiple SM equal to PRE by PCY. This is receiver power at a design point. Okay, and this is the cycle input, the nominal cycle input power. Okay, that's all. Thank you.